Hey everybody, it's Ms. Phoebus, and I'm back with another lesson, lesson 58, rewriting and solving exponential equations. Our learning goals for today: I can use properties of exponents to transform simple expressions for exponential functions, and I can solve exponential equations in one variable. We are going to, according to our state standards, need to be able to use the properties of exponents to rewrite exponential expressions. And they want us to be able to not only solve, but also provide like steps on how to solve exponential equations with integer exponents. And we're going to turn in our notes to page 295. And when you're there, we're going to recall the properties of exponents. And what I want you to do is I want you to pause the video and try to fill in the product rule, the quotient rule, the power to power rule, and the product to power rule. All right, the product rule: if I have two bases that are the same and they are multiplied, I can add their exponents. The quotient rule: if I have two bases that are the same that are being divided, I can subtract their exponents. Power to power rule: if I have something raised to a power, I multiply the exponents. And product to a power rule: each piece inside gets its own exponent, and it gets multiplied by that exponent on the outside. The guys inside there, the x and the y, that exponent 1. Now, my next question is, did you know that not only can you take the stuff that's written in black and rewrite it like the stuff in red, you can also go backwards. You can start with the stuff in red and rewrite it like the stuff in black if you need to. So that is something, these are called identities. That is something that is true, that you can have it written one way, either the black or in the red, and be able to rewrite it the other way if you need to. All right, so our goal is to simplify exponential expressions, trying to write them with only one base. Maybe not necessarily a positive exponent, just kind of depends on what's going on, but the goal is to write it with only one base. In the homework, I am going to give you a specific base to write for. So here we're just going to kind of go with what we see, and I might show you a couple different things. But we're going to be assigned like a base of 2 or a base of 3 in the homework that you have to rewrite these in. All right, so I have 17 to the p times 17 to the q. I notice my bases are the same, right? They're both 17. And because I'm multiplying, I can use the product rule to show that I'm going to have 17 to the p plus q. And that is the product rule. Okay, so notice that I have one base. I have both parts of my exponents together in a new exponent, but notice that they're not multiplied, right? Because it does say 17 to the p times 17 to the q. I can't just multiply them because that product rule says I have to add my exponents. So how I put them together is important. All right, let's look at number 2. We've got 5 to the negative third to the x minus 2 power. So this is definitely a power to a power rule. And that means that we're going to multiply. Now, when we multiply, notice that we have a single number in the exponent on the inside and then a binomial exponent on the outside. So when I go to write this multiplication, I want to wrap this in parentheses because I'm going to have to use the distributive property. So we're going to do 5 to the negative third times x minus 2. And then we're going to distribute. So we're going to end up with 5 to the negative 3x. What's that? Plus 6. Now, that is one way to write this, but there's another way. Using the product rule that I have here, I could separate these and turn them into 5 to the negative 3x times 5 to the 6. Now, some people might be like, well, why would you want to do that? Well, again, it's just another way to write it, but 5 to the 6 is something that I can evaluate, something I can turn into another number, and I could change this into the 15,625 times 5 to the negative 3x. I could also do something with that 5 to the negative third. So the thing is that there's lots of stuff going on and lots of possibilities. If I'm trying to just write it with only one base, then this might be the way to go. But maybe I want to see, is there a vertical stretch or compression? Is it an exponential growth or a decay? So I could even evaluate this piece and do that, throw it in the denominator thing. So there are lots of ways that you can write this, and I just want to show you 1 over 3, 5 to the third is 125 to the x. So we have lots of ways that we can write this, and that's why they have like those multiple select options, because it's like, what can you do? What are you allowed to do? And so there may be a whole bunch of different ways you can write it. So we have this 5 to the negative 3x plus 6. That is one way to write it. You could write it again as this 15,625 times 5 to the negative 3x. You could write this as 15,625 times 1 over 125. It's kind of blended in to the x power. So there's multiple ways to write it. It depends on your end game. Okay, but that's what we're doing. We're just exploring what kind of capabilities that we have and what kind of things that we're allowed to do. All right, so here we have another one, 9 to the 2x times 3 to the 1 minus x. Now let's go ahead and play around with that idea of, let's get it to a single base, then maybe we might end up doing something else with it. Now 9 and 3 are not the same base, but I can rewrite 9 so that it does have a base of a 3. So 9 is 3 to the second power. So I'm going to rewrite, let me do this right underneath. I'm going to rewrite 9 as 3 squared, and that's still to the 2x, times 3 to the 1 minus x. Okay, so all I'm doing is I'm replacing 9 with 3 squared. Now, I'm kind of in this boat right here, this power to a power piece right here. So I can multiply those exponents. So I got power to power is what I'm using. And let's rewrite that. We're going to write this in the solution box. So we're going to multiply. It's going to be 3 to the 4x, because that's what 2 times 2x is, times 3 to the 1 minus x. And now that those have the same base, now I can pull them together using the product rule into one base with an exponent. So that means I'm going to have 3 to the 4x plus 1 minus x, and we can simplify that. We're going to combine like terms. 4x minus x is 3x, so this is 3 to the 3x plus 1. So that could possibly be an answer, but remember, we did split this exponent up last time. We took it where we had two things being added and we broke it up into two things being multiplied. So we could do that. We could do 3 to the 3x times 3 to the first power, just 3. So we might get something that looks like 3 times 3 to the 3x. So this just writes it like with the 3 in the front, so it's got like that exponential, that vertical stretch, if you wanted to think of this like graphing wise. I really feel like we could do something with that 3 to the third part, and I think we might evaluate this piece. Just go ahead and turn that into something. So another way we could write this is 3 times 3 to the third is 27. 27 to the x. So I've got that blue box, I've got this red box here, And I've got this, let's do an orange box. All of these, and even the beginning piece, are all the same. And I want to show you that. I want to break out the calculator. I want to show you that these are all the same. So, calculator time. Here we go. And so we've got, let's do 3 to the 3x plus 1. And then we've got 3 times 3 to the 3x. And then we've got 3 times 27 to the x. And then we could even go back and put the original, and we might do that in a second. But we can graph. And if you look, they're all the same. If you go to the table, they're all the same y values. Let's go in and put the original in. I thought we could do that too. But you want to check or double check or anything like that, this is very helpful. All right, times 3 to the 1 minus x. Let's get the last one in there. And there it is, right on top. Everything's there. All 4 of them. Whoop, all 4 of them match. How crazy is that? So we can write it a whole bunch of different ways, and they are all the same. And so that's where that multiple select feature comes in. It's like, okay, which way can I write this? Well, you could do a little bit of that, you could do a little bit of that, you could do a little bit of that. Depends on what you want. What is your end goal? So in the homework, your end goal is to write it with only one base. That's your end goal. But I want you to see and experience and watch and even do maybe a little bit of what else can we do? And what else can we do with that? Is there anything else we can do with that? And how can we do this? And, and all of that stuff, pulling it all together, okay? So that was number 3. Let's look at number 4. All right, so we've got 16 to the p times 1/4 to the 2p plus 3. So we want to write them with the same base. And you have actually a couple options here. 16 and 1/4 are both a base of 2, but they can also both be written with a base of 4. So at this point, especially since it's kind of open-ended, we have some options. Let's go ahead and let's write this with, let's go ahead and do a base of 4. But usually, a lot of times we go back to a base of 2. So we might even look at that maybe a little bit more when we simplify. But 16 is 4 squared. And 1/4 is 4 to the negative 1. So that negative takes it from being a fraction back to being a whole number. All right, so then now I'm going to use the power to a power rule to change the 4 squared to the p to 4 to the 2p. And I'm also going to use it to do the same thing for the other part. We're going to do 4 to the negative 1 or negative 2p plus 3, and then we're going to distribute that. So this is going to be 4 to the 2p times 4 to the negative 2p minus 3. So that was the power to power rule. Always like this lesson, these types of lessons with power to the power rule. My maiden name was Powers, and so I always like, yay, powers to powers. All right, so for this piece, what we're going to do is we're going to now use our product rule, and we are going to combine those by adding. So we're going to have 4 to the 2p plus negative 2p, which, ooh, we could do something with that. That's going to end up canceling, right? And it's going to be 0 minus 3, and 0 minus 3 is negative 3. And then we can rewrite that as 1 over 4 cubed. 4 cubed is 64, so 1 over 64. So that like simplified completely. There was no variables in there at all whatsoever. And unless you were doing this sort of thing, you wouldn't know that it didn't have variables. All right, let's look at another one. Okay, so this one's got a little bit of division, so we're definitely using the quotient rule, but I can't do anything with it quite yet because we don't have them with the same base. So let's change 27. 27 is 3 to the third. So I'm going to change 27 to 3 to the third to the 2x over 3 to the 4x. Now I've got this times 4 to the x. I'm going to do something with that in a little bit. Which you may be like, I don't know what you're going to do with it, but we're going to figure something out because I can't write 4 with a base of 3. Anyway, let's do our power to a power rule, and we'll end up multiplying these guys. So this will be 3 to the 6x over 3 to the 4x times 4 to the x. And then I'm going to subtract, so I'm going to have 3 to the 6x minus 4x times 4 to the x equals, I might come up here, kind of running out of room a little bit, come up here and do 3 to the 2x times 4x, 4 to the x. And then, well, if I had the same exponent, then I could pull this back together here. So if I could turn that 2x into just an x, which I can by looking at just the 3 squared part. 3 squared is 9. So this is 9 to the x times 4 to the x. Then what I can do is I can pull them back together and do 9 times 4 to the x, which is 36 to the x. How beautiful is that? Nice. All right, we didn't write our rules. Let's see. We use the quotient. We use the product to a power. And then we did our power to power. Okay, so it's just like, what do you see? What do you notice? What else can you do? What? And that's why I have these up here at the top, because we keep referring back to them. All right, so determine if each expression is equivalent to the expressions below. Now, some people, they like to play with the answers. I like to play around with the problem and try to get it to look like the answer. So what we're going to do is we're going to try to pull these together. Looks like we've got some different things. And actually, I want to look at the answer for just a second. Look at this. If I did this piece, just the 2 squared, wouldn't I get 4? And it would still be raised to the m? That's interesting. And then, I wonder what 16 to the 0.5, just like we did 2 squared, what's 16 to the 0.5 power? Have you ever put a fraction in as a, ooh, this right here becomes 4. So these are all the same, 4 to the m. So the question is, what does this turn into? That's what the question is, because if it turns into one of the things that we have here, they're all equivalent. Now, it is possible that they're not all equivalent. So let's look. I would probably go with, I wrote this, so it should be equivalent. But just looking at my answers, I can see, especially with the where I just raised the number to the number part that's being multiplied times that power. Can't do it like if I'm adding or anything like that, but if it's multiplying, that does work out. All right, so let's look at 64. Let's try to write with a base of 4. 64 is 4 to the third. And then we have this 4 to the 2m. So that ends up being 4 to the 3m over 4 to the 2m. And then we would subtract 4 to the 3m minus 2m is 4 to the m, which that's what we have here. But we already know that this is also equivalent and this is also equivalent. So that's what we're doing. We're playing around. So you can look at the answers a little bit. Ooh, look at this one. So this is the one where it says xy to the m equals x to the m, y to the m. So when my exponents match, I can pull the bases in together, so like here, and then I can write it with one of those. And then 3 times 4 is 12, so this is 12 to the 2m, which I have right here. But 12 to the 2m and 12 to the 4m, I don't think we can write those the same because nothing is really going to be able to change there. Question is, what about this 144m? So look here. What's 12 squared? 12 squared is 144m, so it's equivalent. So we're just playing around and messing around with stuff. All right. Okay, so I have in number 8, I've got addition, which that means I can break that up. So I can separate it with multiplication. 3 to the t squared times 3 to the 3t. Now I don't see that as an option. I'm close kind of here. Ooh, look here. 3 to the third power is 27, so this is going to be 3 to the t squared times 27 to the t. I'm liking that one. I'd say those are equivalent. I can't do, the t is the piece that's being squared, not the 3, so I can't do what they're trying to get me to do in this 9 to the t times 27 to the t, so that's not equivalent. I'm curious about this other one. It's almost like, you know what they did? And they is me forgetting a parenthesis. They factored 3 to the t times t plus 3. Greatest common factor, right? And then that means that I could write this as 3 to the t plus 3. Equivalent. And you can always check it if you're not 100% sure. All right, so I see division and I'm looking at subtractions on my exponents. I'm looking like that's okay. Definitely have one base, so we want to get these to be the same base. So this would be 7 to the 2m over 49 is 7 squared to the m. So that ends up being 7 to the 2m over 7 to the 2m, which I don't have 1 anywhere, but I should subtract. So 7 to the 2m minus 2m is going to be equivalent, but I don't think we're going to be able to be equivalent there. Now the question is, I don't think the 49 is going to work either, because that would be 49 to the m power if I subtracted, but I should be getting things canceling. Like even here, if I rewrote this as 49 to the m, it's going to be 49 to the m minus m, so that's not going to work either. So you do have to play around with it and see if they are going to be equivalent or not. You can't just go through and go yes or no and just by looking at it. You've got to mess around, try to manipulate these. Otherwise, it's just a guess, you know. So we want to look at trying to figure out what properties do work. All right, so we're going to solve some exponential equations. We are going to use a little bit of what we just did and what we just explored to help us solve those exponential equations. Now, before I do this, I know some of you get help from other sources, some of you get tutoring, some of you go watch other videos, and I'm going to go ahead and tell you this. Do not use logarithms. We do not have to use logarithms. It is not in our standards. I don't want to see the word logarithm. I don't want to see log. I don't want you using it in the calculator. We are going to use same base. Okay, that's what we're going to do. We're going to do same base stuff. So there is no need for logarithms at all. None. And I want to see your work. And if your work has logarithms in it, not good. Okay, and I will be writing that in the notes. I told you not to use logarithms, -5. You just lose the whole entire thing. Don't do it, okay? That's not the point. The point is to be able to do it without logarithms. Now, not every problem can be solved without logarithms. Every problem that I will give you can be. All right, so here we go. You're going to isolate the base that has the variable. Now, some of them have variables on both sides, and we'll talk about that. But you're going to get the piece that has the base by itself with the variable. Then you're going to rewrite both sides of the equation with the same base. So remember how we wrote 9 as 3 squared to make those bases match? Same idea. Then we're going to set the exponents equal to each other, solve for x, and then it's recommended that you check your solution. And how do you check a solution? You take that value, that variable, you plug it in, does it work? So here we go. We're going to start off easy and then we'll work our way up a little bit. So we're going to start with the bases matching. So in number 1, do you see how both bases are 6s? So because both bases are 6s, I pretty much get to get rid of those 6s and focus just on the exponents. And we want the exponents to be equal to each other so that we can solve for x and get x equals -2. And then we're going to check. I'm going to do check in a different color. So this is going to be 6 to the -2 plus 5 equals 6 to the third. Does 6 to the third equal 6 to the third? Absolutely, it checks out. And then 6 to the third is 216 equals 216. Yes, okay? So that's what we're doing. Now, it starts off easy, right? That always changes as you go through and you're learning it. So we're starting off easy, and then we're going to maybe have some more complications along the way, but it's going to be okay. But that's the general idea of this. Okay, so let's look at example 2. Do you think you could figure out how to work example 2? Try pausing the video and see what you can do. All right, let's look at this. So both of them have the same base, so we get rid of the base and we focus on the exponent. We're going to add 5 to both sides. X equals 13. You can check if you like. 15 to the 13 minus 5. Does it equal 15 to the 8th? Yes, it does. I don't want to figure out what 15 to the 8th is, but 15 to the 8th equals 15 to the 8th, so guess what? It checks out and we are good. We got an answer. All right, now let's switch it up a little bit. Let's look at example 3. Now, the bases don't match, but let's think about 1. 1 is kind of special. Is there a way to write a 1 so that I have a base of 3? How about 3 to the 0 power? Anything to the 0 power is 1? All right, so what we're going to do is we're going to get rid of the bases. We're going to say 2x equals 0. What is x? X is 0, and we can check. 3 to the 2 times 0. Is that 1? Well, it's 3 to the 0. 3 to the 0 is 1. We're good. It checks out. So when the bases are not the same, the goal is to rewrite the bases so that they are the same. So that brings us to example 4. We now have, and I really don't like the way that it's written. Let's write it like this. Okay, so I've got 5 to the x is equal to 1 over 125. So I want to rewrite 1 over 125 as 5 to some power. And so what I'm going to do is I'm going to think about, well, what about 5 to what power gives me just a plain old 125? So 5 to the third power is 125. And you might have to play around in your calculator with that. What's 5 squared? What's 5 cubed? What's 5 to the fourth? You know, play around and type numbers in. Now, how do I get it to go to the denominator is the question. Do you remember? We need a negative. So this is going to be 5 to the x equals 5 to the -3. And I like these because, bam, bam, x equals -3. And you can plug it in and check it. All right, let's do another one. Example 5. Do you have any ideas where we should start? We're going to rewrite 49. 49 has to have a base of 7. And 49 is 7 squared. Get rid of your bases. Bam, bam. We've got 3x equaling 2. So x equals 2/3. And that's it. We're done. other than checking, and you can check. All right, let's look at example 6. We want them to have the same base. I'm going to go with a base of 2, so I can rewrite that 4 as 2 squared. So I'm going to rewrite this. 4 is 2 squared. Okay, and then we are going to do what we did in that other part where we end up multiplying these guys together. But I'm going to wrap this one in parentheses so I can remember to distribute. So that's going to be 2 to the x plus 3 equals 2 to the 2 times x minus 2. And then we're going to distribute 2 to the 2x minus 4. We're going to cancel, cancel, cancel. We've got x plus 3 equaling 2x minus 4. And now we're like back to like unit 1, lesson 1 pretty much. We're going to solve for x. All right, get rid of that, get rid of that. 7 equals x. And that's our answer. To make the bases match, set the exponents equal to each other, solve for x. That's it. So, 7. We're going to try number 7. Now, the question is, they don't match right now. What are we going to do? And I'm thinking, a lot of times it always goes back to like bases of 2 and 3. And 1/4 has a base that I can write with a 2, and 32 has a base I can write with a 2. So let's see. 1/4 is 2 to the negative 2 power. 32 is 2 to the 5th power. And then I'm just going to, because I'm going to multiply. I'm going to multiply these guys. Don't forget my parentheses, right? Multiply those. And then really, at that point, the bases are going to cancel. So I'm going to go ahead and just write it like this. Negative 2 times 9x minus 5 equals 5 times x plus 8. So save the whole canceling bases later. Just go ahead and bring that up earlier. All right, we are going to distribute. And then we're going to work on solving for x. And sometimes these numbers aren't very nice. So just keep that in mind. Sometimes they'll be fractions. 30 looks like we've got x equals negative 30 over 23. How beautiful is that? All right, let's look at number 8. Now, number 8 is a little bit different because we addition around our base. So this is where step 1 in the steps I was talking about, isolating that base with the exponent, that's where this comes in. So if I have any additional addition or multiplication or subtraction or anything like that, I want to get this base by itself. So I'm going to move this 2 by subtracting it. 3 to the 2x minus 3 equals 9, and 9 is something that I can write with a base of 3. 9 is 3 squared, and then now my base is matched, so I can have 2x minus 3 equals 2, and I can start solving for x. X is 5/2. So that's what you do when you have other pieces around your base. You shouldn't have ones with x's on both sides and then extra numbers. That's probably not going to happen unless they have the same base and can be worked in. But I'm not going to do that to you. All right, I think these are the last 2 that we're going to do, and that'll be the end of the video. And you'll be getting ready for your test, right? So here we go. Example 9. I cannot multiply this 2 and this 7 together. It's not going to work. So I need to divide by 2. And that's helpful anyway, because guess what? 14 divided by 2 is 7. I've got a base of 7. If I'm getting ready to solve for things and I can't get my bases to match, I want to look for issues that I have maybe somewhere else. Now that's 7 to the 1st power, so I'm going to say x plus 5 equals 1, so x equals negative 4. All right, so example 10, you want to try pause the video, see what you can do. All right, so what we're going to do is we're going to treat this piece like we're isolating it, like it's a variable. And how would we do that? Well, we would first add 8. 2 to the 3x over 4 equals 18. Divide both sides by 2. 3 to the x over 4 equals 9. And then now 3 to the x over 4 equals 9 is 3 squared. If x over 4 equals 2, then what does x equal? X equals 8. All right, guys, that's it. So you've got a lot of things to look at. You have stuff from Unit 5 and 6 and 7, so I'd be flipping through all my notes, making sure that I'm well acquainted with factoring and quadratic formula, and looking at graphs of quadratics, looking at systems of equations, where do two lines cross, substitution, elimination, what if I gave you a parabola and a line to see where they cross. Let's see, and then all of your arithmetic and geometric sequences, and your recursive and explicit functions, and graphing exponential functions, all of this stuff. It's like coming together, and we're going to take a test on it tomorrow, so make sure you're ready. If you got any questions, come join me in a Google Meet. I'll see you later. Bye, guys!